Hello and welcome to our next lesson in our greenhouse gases environmental lesson. We had left just talking about energy balance and the direct relationship between the levels of carbon dioxide and the warming of the atmosphere at the Earth's surface. And we're looking specifically in our next lesson, how do these specific gases go about trapping the heat energy from the sun and thus warming up the environment nearest the Earth? So it all lies in the geometry of the molecules, and this section is called molecules and how they shape up. What is it about a molecule of carbon dioxide, a molecule of water, a molecule of methane, CH4? All of these specific molecules are said to be greenhouse gases, whereas nitrogen, the most abundant gas in our atmosphere, is not considered to be a greenhouse gas, and that's also true for molecular oxygen. It is not considered to be a greenhouse gas, although ozone would be. Well, the secret of that answer lies in their shape, the geometry of the molecule. How does it physically look in a three-dimensional world? We'll look at its Lewis dot structure, which we practiced in our last section together in our previous chapter, and we'll look again at how those atoms arrange their shapes in a three-dimensional world. It's known as the valence shell electron pair repulsion theory, commonly called the Vesper theory. Valence shell electron pair repulsion theory. In essence, since electrons are all negatively charged, electrons want to spread themselves out from each other as far as possible because we know like charges repel. So these geometric shapes of the molecules, as we explore them, will start to give us great insight into the types of bonds and why they're able to store energy. So let's just remind ourselves a little previous lesson. We know if we were to just draw the Lewis dot structure for a molecule called carbon dioxide, we know that carbon lives in group 4A, so it has 4 valence electrons, and we would start by just placing a dot, one around each side first. We know that oxygen lives in group 2A. I'm sorry, I read that too. Oxygen lives in group 6A, and I wrote 6, but I said 2. But there's 2 of them there for a total of 12. 12 electrons, valence electrons from both of the oxygens, giving us 12 plus 4 is 16 dots altogether. So we have 16 electrons. Remember, the goal as we start to build atoms into molecules, the way that they bond together, they all want to create an octet, that magic number 8. So here we place an oxygen next to carbon and we're starting to build a carbon dioxide molecule. One around each side first, and then I go back and assign partners. There is the first single bond between the atoms of carbon and oxygen. And we would know to think symmetry, so the second oxygen would go to the left side, and with its 6 valence electrons, we build it such as this, and we have a shared pair of electrons. But we understand just visually we're not done yet. We have 2 electrons that are not yet partnered on carbon, one over here that's lonely on the oxygen, one more that's lonely over here. So we said the best thing to do is to bring those into the center and share what we made as what's called a double covalent bond. So sharing that pair of electrons to create a shared pair. So just cleaning that up, we know it was O, double bond C, double bond O, and we had 2 lone pairs on the outside oxygen. So just quick review of what we practiced in our last chapter. What is the shape of this molecule, and how is it so good at absorbing heat energy? So remember, we have energy. The ultimate source of energy comes from the sun. And if I just think about what types of energy are coming down from the sun, we start to see it radiate down and at the atmosphere near the Earth's surface. We know that there would be UV radiation hitting, ultraviolet, which we know comes in 3 flavors, UVA, UVB, and UVC. We also has the visible light spectrum. The visible light is Roy G. Biv, those colors of the rainbow that we see. And we also have what's called IR, infrared radiation. And I wrote them like this on purpose. The highest type of energy, the most energetic, the very short wavelengths is UV. Visible is about 10 to the negative ninth nanometers. And then this is the lowest energy with the longest wavelengths, known as IR. Infrared, just kind of thinking about a heat lamp uses infrared radiation. What happens is that the energy from the sun in these polar bonds, and we're going to talk about what I'm just saying here, polar bonds, and I'll talk about that in a minute, but what they do is act as a reservoir where the IR radiation gets trapped inside of these bonds. So let's kind of talk first of all how it does that. Think of this bond right here as a spring. Literally, if I have a spring between the carbon and the oxygen, a spring can be stretched, a spring can be compressed, and a spring can be twirled around and bent in different directions. This ability to move back and forth and vibrate is how the infrared radiation gets stored in the bond between the carbon and the oxygen, and both sides. I keep pointing to one side, but it's actually both sides. The reason it can is because of the electron distribution in this bond. The carbon is not as strong as compared to the oxygen in pulling the shared pairs of electrons towards itself. Since oxygen is just a little bit more polar, a little bit more strong compared to the carbon, it's able to pull the electron density away from it, and if you're stretching the bond, that's the site where the UV radiation can be stored as heat energy. And if the carbon dioxide gets trapped in the atmosphere and it's storing heat energy from the sun, we're going to see a direct relationship between increased CO2 levels and increased temperature at the surface of the Earth. In terms of the geometry of this molecule, just think about it. We have a carbon, we have two oxygens on each side. It's very much like a straight line. This particular molecule is said to be linear. A straight line across, where we would have what's called a bond angle from one side to the other as being a straight line. 180 degrees would be the bond angle as a straight line. The molecule itself, these bonds have to have the ability to vibrate back and forth in order to create the situation where we can absorb the UV radiation, the visible, and the IR. Now remember, we just finished a little while ago in our last lesson talk about energy balance. The amount of radiation coming from the sun, if it's in balance, will return the exact same amount. Well, what if we start having an increased amount of carbon dioxide in the atmosphere, and instead of having this much energy hit, we only return this much energy? And all of the excess that's stored or trapped in the atmosphere is the place that we're gaining more and more heat energy, causing the surface of the Earth to warm up. Carbon dioxide has the ability to trap energy in its bonds by the vibrational back and forth pulling and stretching. Water also has this ability. Now let's just talk, and I should probably extend the page. I'll draw a water molecule and talk about its molecular geometry. Oxygen with its 6 valence electrons and hydrogen with its 1 valence electron form a molecule that actually looks in 3 dimensions like this. The electron distribution is very dense around the oxygen atom. The electron distribution on the hydrogen is scarce. That makes these bonds vibrate and twist just as a spring would. Remember my spring analogy. I can stretch it, I can compress it, I can twist it, and I can, anything you can do to a slinky, these bonds behave in the same way. The electron distribution out here on the oxygen makes this region very negative. The electron distribution here, since it's lacking, makes this region of the molecule very positive. This is what we refer to as a polar molecule. Just like a bar magnet. If you've been in a science class and looked at a bar magnet, you see stamped on one side a positive, stamped on the other side is a negative. Just like a battery terminal has a positive and a negative. If it's in the same structure, it's said to be a dipole because we have two different charges within the same structure, positive and negative. It's all being the same idea here in terms of the water molecule. Water, and I look at the symmetry around this oxygen. The oxygen, which is our central atom, has 2 unbonded pairs of electrons and 2 bonded pairs of electrons. And when we see a molecule built like this, we have 4 total domains of electrons around the central atom. Of the total of 4 domains, 2 are bonded and 2 are unbonded. The molecule has a molecular geometry that's said to be bent. It's not flat, like carbon dioxide. Let's take a look why. Notice here, carbon dioxide, by the time we were done drawing it, it had no electron pairs left that were unbonded. It only had bonded pairs. It formed a very straight line known as a linear geometry. However, water, its molecular geometry had 2 lone pairs and 2 pairs that were bonded. When this happens, the molecule is said to be bent in its geometry. And you'll see this approximately 109, 104.5, but the electrons kind of push it aside, somewhere close to 104.5 degrees in terms of the bond angle between H and H. There was one more molecule listed on this page, and it was methane. Here's methane, CH4. Carbon with its 4 valence electrons, all hooking back to that central atom. This molecule at first glance might look flat, but what does it really look like in terms of its molecular geometry? Well, let's first talk about these bonds between the C and the H have an unequal electron distribution. They are said to be polar bonds. That means hydrogen, who is not as strong at pulling the electrons towards itself, and carbon, who is much stronger at pulling electrons towards itself, you're starting to see the electron distribution all being pulled towards the carbon. The bonds are polar, an unequal distribution of the electrons in the shared pair. When I tell you that bonds are polar, what that tells me is that these bonds, just like a spring, they can be stretched, they can be compressed, they can be twisted around, and when that happens, they're using and storing infrared energy from the sun. So the more and more methane molecules that are occurring in our atmosphere, the more storage tanks there are to keep the excess heat energy from the sun nearest the earth and thus warm up our temperature. We also mentioned that nitrogen and oxygen are not greenhouse gases. The most abundant gas in our atmosphere is diatomic nitrogen, and as we drew that last chapter, we realized that nitrogen, just 2 atoms of nitrogen bonded together, had a triple bond, and molecular oxygen had a double bond. Well, when I consider this perfectly, those are 2 dots, that didn't come out well. When I have one atom identically bonded to another atom, N bonded to itself, there is no atom stronger or weaker as compared to the other. This is said to be a non-polar bond because we have an equal distribution of electron density between the 2 ends. Nobody can tug of war this shared pair. They're equally distributed. And because it's a non-polar, equal distribution, this molecule does not store energy. So I should have drawn that different. I'll go infrared. Nope. It has no ability to store the energy from the sun because it's a nonpolar bond. We'd say the same thing for oxygen. An O bonded to an O, they're both identical atoms. Nobody would be stronger or weaker, so we have a very equal electron distribution between the 2 atoms, making this bond non-polar. and therefore does not have the ability to store and keep infrared radiation and thus warm up as a greenhouse gas. So here's a picture of kind of things that we've just talked about, and I got ahead, but this is kind of a nice debriefing of that molecule drawing we were doing. Sometimes, if we have a number of bonds, such as carbon dioxide, we have two bonds, one going in the direction of each oxygen. Think of that double bond as just one direction. The only choice of that molecule is to be linear. Carbon dioxide is a greenhouse gas because these bonds can be stretched and vibrated, and thus store IR radiation. Sometimes we have molecules that have three bonds, or two bonds with one lone pair, and they look like a triangle, literally a trigonal planar geometry. Ozone is an example of this molecule as well. Ozone has a trigonal planar geometry. When I referred to that, we talked about ozone with its resonance structure, and I can kind of show that delocalization. Notice how we had around the central atom of ozone from our last chapter, focusing on the central atom, notice how there's one unbonded pair of electrons, that one lone pair up here, and then two bonds going in the opposite direction. Of the three total domains, I have one up, one left, one right. It says there are, right here, there's one unbonded pair and two bonded pair. We have a bent geometry. See how I drew that bent? If I had a molecule that had another attachment up here around the central atom, I have 1, 2, 3 domains. The number of bonds is 3, but I have no lone pairs on that central atom. That's when we refer to it as trigonal planar, lying flat in a plane. And of course this bond angle would be 120 degrees. This is what we drew for methane, our CH4, and I said if you can envision this not as a flat molecule but more as a tetrahedron, you will have a better 3D image of the methane molecule. So in the center we have this carbon, and we have like 3 legs pointing down and one pointing up. And I can twist and turn all of these molecules around and have the same geometric shape. The bond angle here we said was 104.5 degrees. Bond angle here we said was 120. The bond angle here was 180. Methane doesn't look like this. In reality, if I try to draw methane, I have a hydrogen sticking straight up like a flagpole and 3 more that are kind of pointing down, creating a leg, kind of like it would support the center atom, like a 3-pronged, well, you know what, they're going to show us a picture of like a music stand. A music stand with its 3 legs supports a sheet of music up here. This would be the carbon and 3 H's. And we're getting a visual of what the tetrahedron shape looks like. If I take off one of the bonded elements and take a lone pair there, there's still 4 domains, but 3 are bonded and 1 is not. It's now known as trigonal pyramidal. And just like a water molecule, if I had 4 total domains, 2 bonded, 2 not bonded, now it's still considered to be bent. We could have 3 domains being bent, like ozone, or 4 domains being bent, like a water molecule. So our goal is try to imagine these molecules best we can in 3 dimensions. We've been practicing, some kind of sneaky that way, how to draw Lewis dot structures. And as we draw Lewis dot structures, we remember the goal is to have 8 electrons. Unless you're hydrogen, then it's just 2 because its noble gas is helium. And we have practiced drawing these to where by now you're recognizing just by the simple molecule what it looks like. Molecular oxygen. Of course, this would be a linear molecule simply because 2 points, 2 dots connected make a straight line. So the bond angle here has to be 180 degrees. Methane we drew just a moment ago. Methane, we said, would be tetrahedral because all 4 domains are bonded. A tetrahedral, remember this? All 4 are bonded, giving us a tetrahedral shape. This molecule looks like this as a spatial arrangement. We would call it tetrahedral with a bond angle of about 104.5. It could be 109 depending upon really if there's electrons pushing this around. So somewhere between 104.5 and 109 or 109.5, somewhere in there. But those are pretty close numbers, aren't they? If we had sulfur dioxide, you would end up having, well, let's draw it together. 1, 2, 3, 4, 5, 6 electrons around the sulfur. Oxygen also has 6. 1, 2, 3, 4, 5, 6. There's a bond. And 1, 2, 3, 4, 5, 6. There's a bond. Lonely electron, but I am only allowed to switch back between the central atom. So here's a situation where I'm going to erase one of these electrons from the oxygen, and I'm going to bring it in to the center and rearrange so that we still have the number of electrons correct. Now remember what we're doing? We have 6 times 3. Let's start over. We have a total of 18 dots, right? 6 from each of these elements. They all live in group 6A. When I start with 18 and I connect them with single lines, I've used up 4. That gives me 14 dots left. Then the rule says place the octet around all of the atoms that are not the central. That would leave me 12. So 2 more to go. That's where I place them like this. So that's kind of the step I took here, was just kind of getting ready to go here. So placing the 2 dots leave me no dots left, but the sulfur only has 6. So that's why I was saying we have to erase a pair of electrons from the oxygen, and that's my clue that I know I need a multiple bond in one direction. Now this is all of my work kind of figuring out what the molecule looks like, but it's not a straight line molecule. It doesn't look like this in nature. What does it look like? Well, that was the purpose of this particular chart, trying to figure out where am I on this molecular geometry. What does the molecule actually look like? If I kind of clean this up. Try, and there we go. So we just drew sulfur dioxide. It had 3 domains total, but only of the 3, only 2 were bonded and 1 was not. This molecule is said to be bent with a 120-degree bond angle, as in a trigonal planar overall geometry. Of the 3 domains, 2 was bonded, 1 was not. So let's verify that. Here's the sulfur. 1, 2, 3 directions. There's 3 total domains. Of the 3, 2 are bonded, 1 is not. This is a bent molecule. So if I really wanted to show this, I should make the geometry look more like a triangle with a lone pair. This would be 120 degrees, not 180 as I had drawn it here. So that's the whole goal here, is trying to decide, is a molecule going to be active when it absorbs IR radiation? We've had a great talk about this already. Here's a methane molecule giving you 109.5 degrees in what we refer to as a tetrahedral shape. The tetrahedral shape is showing carbon as the central atom, and these hydrogens, there's 3 of them kind of pointing down as legs on a music stand, and 1 pointing straight back up. So these Lewis structures do a great job showing us how the atoms are connected together, but the 3-dimensional view is known as the Vesper Theory, valence shell electron pair repulsion theory. We want to spread the atoms out as far as we can and get a better visual as what they look like in nature. So the tetrahedral shape has a bond angle of 109.5 tetrahedral. And here's that music stand that I had talked about. See that carbon in the center? I look up, look left, look down, look over here. See the pyramid in there? So when we say that it is a tetrahedral shape, you can see that it has the 4 sides, 1, 2, 3, 4 sides in this particular slide. And I also get a better visual. If this is the carbon on the music stand, this would be the hydrogen pointing down and the other hydrogen pointing straight up. Not a flat molecule at all, but more like a music stand. So the 3D shape of a molecule directly affects its ability to absorb infrared radiation. So remembering that we're assuming the most stable molecular shape has the electrons surrounded a central atom as far apart from one another as possible. So we want to spread them out to give room for like charges that repel each other. And what we've been practicing is making sure we give the space to the electrons. So why isn't water a linear molecule? The electrons around this central atom are actually farther apart if we give them 104.5 degrees between them instead of having them exactly on top and bottom. So the bonding and 2 non-bonding pairs, they actually take up more space than bonding pairs. And so therefore we start to compress the angle and we start to create a bent molecule. I have more space by bending the molecule than by having them straight across from one another. So the space between here to here is only 180 degrees, right? That's 180, but we're packing in the electrons right on top of each other. If we get these hydrogens closer together, we're giving more space to the electron cloud to spread the electrons out. I can see this 180 is clearly not as great of a distance as all the space up here. I'm allowing the electrons to move away from one another with my bent structure. So here we have a bent shape of a water molecule. If I have all 4 pairs of electrons around the central atom involved in a bond, we call it tetrahedral. And that tetrahedral has a bond angle of 109.5. If the 4 electrons around a central atom have 3 bonded but 1 non-bonded pair, it's said to be, I call it trigonal pyramidal, triangular pyramid. And if it's of the 4, 2 are bonded and 2 are not, we said to be bent. Now this I would suggest to you is in this earlier slide. They're just presenting it again in a different way. Notice this is all of those words right here. I could have tetrahedral with 4 electron clouds. I could have trigonal pyramidal, they called it triangle pyramid, where I have a lone pair and 3 bonds. Or I could have a bent structure on the central atom if I have 2 that are unbonded and 2 that are bonded. So all of these with 4 domains, or the central atom has 4 things to look at. The molecular geometry could be tetrahedral, trigonal pyramidal, or bent. One more. So that's what this slide was showing for us. Now look at the central atom of carbon dioxide. Carbon dioxide has no lone pair. Carbon dioxide has only bonds around it, therefore it's said to be 180. It is a linear molecule. And these linear molecules, such as carbon dioxide, have this great ability to stretch and compress and twist and bend, and when they do so, they have the ability to absorb for IR radiation, just as we discussed. If I have a polar bond and the springs between the atoms can be stretched, twisted, and pulled due to the polarity of the bond, if this is carbon dioxide, oxygen has a greater hold on the electrons being shared, pulling the electron density towards itself, creates a spot for the IR radiation from the sun to be absorbed. And that's what they're showing here with this spectrum. The IR spectrum, infrared spectrum for carbon dioxide. And all it is really a graph. what we do is it's just a machine in the chemistry lab, and I place a sample by injection into the machine, and it hits it with a source, a laser source of IR radiation, infrared radiation. And we just have a graph, literally, that prints out the opposite side. We have what's called percent transmittance on the y-axis and something known as wave numbers on the x-axis. And all that is a reference to is the strength or the distance of the wave. So again, if a wave number is long or is the wave number short, we get a little different view of the energy. And anytime we see some stretching of the molecule bonds or some bending of the molecule bond, we'll start to see a little energy action where the IR is being absorbed, and we'll see how much it is. So perhaps this would be the C, and just think of it as a spring attached to the oxygen, and if I'm stretching it, I'm pulling the spring, and that's absorbing energy. And if I'm bending the spring, just think of it as twisting the spring, then I can see that's an absorption of infrared energy. And that's all that's being picked up on an infrared spectrum, is the vibrations like a spring in a polar bond. And that tells us exactly where the infrared radiation is being stored from the sun, upsetting the energy balance here on near the Earth's surface. So the stretching and the bending absorb IR radiation. We can pick that up using a machine called an infrared spectrometer, giving us a graph called infrared spectrum for carbon dioxide. So the IR radiation is absorbed, and the amount of radiation that makes it through the sample is reduced, and therefore we have percent transmittance on the graph. So what do I need to know from this? Just understanding that bonds truly are energy, have the ability to store energy. So I tried to draw this earlier. Just keep in mind this is the electromagnetic spectrum. And if this is a carbon dioxide molecule, keep in mind there's different types of radiation. Remember over here is a real high energy called UV, ultraviolet. Comes in 3 different flavors, UVA, UVB, and UVC. Any one of those 3 that when it hits a chemical bond, it's so energetic, it just breaks the bond apart. That's exactly what was happening when ozone dissociated into a radical of oxygen and molecular oxygen. We took an ozone molecule, last chapter actually broke a bond apart. Because UV is so energetic, it breaks bonds. But over here, the infrared, which is lower energy due to a longer wavelength, it's not strong enough or energetic enough to break the bond, but just vibrate them, wiggle them back and forth, stretch them, twist them, bend them, and that's what we can pick up on an IR spectrophotometer. So let's review. True or false, this question will say. And these are just highlighted from our chapter. Earth is the only planet that has greenhouse gases. Well, that took us back to a little previous note where I think it was lesson 1, where it talked about Venus, which was 90-some% carbon dioxide and methane in its atmosphere, is a planet that is very much involved with greenhouse gases. So Earth is not the only planet. Venus also has an atmosphere, and that atmosphere contains carbon dioxide and other greenhouse gases, and it exhibits a warming due to that as well. How about our second question? Greenhouse gases in Earth's atmosphere come from both natural and man-made sources. Well, that's true because natural could be something like carbon dioxide or methane, but man-made sources like our chlorofluorocarbons that are our refrigerant molecules that break apart ozone, they're also considered to be greenhouse gases. So they're both. So that's true. Carbon dioxide and methane are greenhouse gases. Yes, that's true. And so is water vapor. Water is also a great storage tank of energy. A greenhouse gas emits and absorbs infrared radiation. Absolutely. That's what we were talking about as a polar bond. Are oxygen and argon greenhouse gases? Well, we decided no, because they do not exhibit polarity in their bonds. They would not absorb infrared radiation. Clearing of forests is one main contributor to the man-made increase of greenhouse gases since the Industrial Revolution. Well, of course that's true, because carbon dioxide, when combined with water, goes back to molecular oxygen, and this is not balanced, and glucose. This is a process known as photosynthesis. So if we don't have photosynthesis occurring, I'll just abbreviate it there, if we remove the plant life of trees, clearing forests, and we prevent this reaction from occurring, we're not putting carbon dioxide back into the molecular oxygen form with stored sugars. This, of course, would increase as we deforest certain areas in our world. What is the main cause of global warming? This looks like one. It's like acid rain, increased concentrations of CO2, the greenhouse effect, and overall increase in Earth's temperature. Well, the main force, or the main cause of global warming, is increasing the CO2, which then creates the greenhouse effect, which then, because it does, traps it in the Earth's environment, in the atmosphere. It's going to increase the Earth's temperature. So this is the cause, and everything else is the effect. If I have this many electron groups around a central atom, I'm asked to understand the bond angle, and this is helpful, the lone pair and how many are bonded, and then what molecular shape. So for instance, the number of electron groups are 2. So I have outer atoms, lone pairs. So let's suppose I have a molecule something like this. Around the central atom, I have 2 electron groups. They are all bonded. There are no lone pairs. So of course this is what we would refer to as a 180-degree, a linear molecule, such as carbon dioxide would be an example there. In our 3 electron domains, we have 2 different geometries. So if I have all 3 bonded, so around my central atom I have 3 all bonded electrons. This is what we refer to as trigonal planar. See the triangle here? An equilateral triangle. So the bond angle would be exactly 120 degrees. But let's suppose I have 2, 1. So in other words, instead of having this bonded up here, I place a lone pair of electrons. Now what does the molecule look like? Well, the molecule now is bent, but the bond angle is still 120 degrees. Ozone would be an example of that, a bent molecule. Ozone has 3 domains, 1 unbonded and 2 bonded. Ozone is bent. If we have 4 domains, we have 3 different geometries. If all 4 are bonded, remember this, if we had a situation where we had something like methane, CH4, it was called tetrahedral. If we removed one of those and we ended up with a lone pair on top, we now call it, you could call it trigonal pyramidal. And the other domain, if we had just 2 electrons bonded, you end up having it bent. So these would be unbonded pairs. So you have tetrahedral, trigonal pyramidal, and bent, all of these with bond angles of 109.5 degrees. We'll do some of these, and I know we've done most of these. I'm trying to find any that are new. Ammonia, NH3. One lone pair of the others are bonded, so 4 domains, 3 bonded, 1 not bonded. We just wrote that in there as trigonal pyramidal. I don't see anything new in here. I really have done all of these already. I'm going to try to find something new to review with. Consider this structure. I have a central atom called Y and 3 attachments. What is the shape of this molecule and what bond angles would we expect? So again, this particular slide you see just so handy when I keep coming back to it way up here at the early part of the lesson. This was pulled from your book. Makes it a very handy, reference table. What geometry am I looking at? So I saw 3 domains. All 3 were bonded to something. I can see it's called trigonal planar, like an equilateral triangle. So the bond angles would end up being 120 degrees. I think that was here. So here I have 120 degrees, and the molecule would be trigonal planar. And you'll see a variety of these in your sapling. So this is an IR spectrum, isn't it? So what type of spectrum is being shown here? Well, it's infrared. UV is too energetic. NMR uses magnets. This is known as an infrared spectrum. Therefore, we're using infrared radiation. And what we're detecting with infrared radiation is really a vibrational frequency of a bond, just like a spring. If we have a carbon-oxygen bond, think of this as a spring, and we're detecting the vibrational frequency as it compresses and stretches and flips around. Approximately 80% of the IR radiation emitted by Earth is trapped by greenhouse gases, causing the warming of Earth's atmosphere known as the greenhouse effect. Nitrogen and oxygen, which are the majority of the atmosphere, about 99%, they're not greenhouse gases. CO2 is a major contributor. So a long-winded question to review. Why is CO2 a greenhouse gas, but nitrogen and oxygen aren't? Does CO2 absorb UV radiation? Does CO2 contribute to the greenhouse effect by absorbing the majority of UV radiation? All infrared radiation is absorbed in the lower atmosphere and does not reach the upper atmosphere where nitrogen and oxygen exist. That makes no sense. CO2 is capable of absorbing infrared radiation. Now, I was kind of being sneaky because this ultraviolet is not what is being, remember this would just simply blow apart the bond? UV is so strong it would break the bond. CO2 and other greenhouse gases absorb the infrared, the less energetic radiation, not that high energy radiation. That was kind of careful reading question. And that's where we'll stop this particular lesson. When we return, we'll be looking at a next lesson, which is quantifying in terms of the amount of carbon in the atmosphere with a term called the chemical mole. Pause here, come on back to your lessons when ready.